I think you can go ahead, Professor. No issue. No,
Okay.
everything working.
Okay, sure. Good afternoon, everyone. So let's proceed to the third lecture, Advanced Metering in Smart Grids. Okay, a second. All right, so before we move to the smart metering, once again, let's have a quick review of the smart grid, right? As we have introduced many times, smart grid has basically three major technical features. At the generation side, we have high-level penetration of the renewable energies, wind, solar, wind power, and solar power. At the demand side, we have new types of the electricity loads, such as electric vehicles and flexible load that can support demand response. And besides, we may also install energy storage system at the distribution network. So these are new elements at the demand side. But on top of it, in order to monitor, operate, and control this system, we need to have advanced information and communication technologies, which are represented by smart meters installed at the household level and the phasor measurement unit installed at the generation plant and transmission grid level. And importantly, these phasor measurement units, they are synchronized by satellite GPS, so they can take the time synchronous measurements of the system. So today, I'm going to introduce two parts at the smart metering site. First one, I will give you a general introduction to the so-called AMI, Advanced Metering Infrastructure. So this one is a kind of communication and metering infrastructure at the household level, which can collect the power and the other information of the customers. And after that, I will introduce the smart meters, which are components under this advanced metering infrastructure. So basically, the data are collected and measured by the smart meters. And under such a AMI infrastructure, the data can be stored, transmitted, communicated with the service provider. And tomorrow, I will introduce the second representative ICT technologies in smart grid, so-called phasor measurement unit, PMU. Compared with the AMI and smart meter, PMU is more for power grid applications, okay, while the AMI and smart meter are more for customer applications. So this is the difference. Everybody, please pay attention to. All right, so before we move to the AMI and the smart meters, let's have a different view of the smart grid. So just now we have introduced the three features of the smart grid, including the generation, new types of the generation, new types of the load, and the advanced ICT infrastructure. But actually, from the for the smart grid, we can actually have a cyber physical view of this system. So why cyber perspective is so important is because yesterday when we talked about several blackout happened in the South America and European many years before. Actually, that blackout was caused by cyber attack. Okay, and yesterday some students have also asked questions about the cyber security, right? Cyber risk. So for the smart grid, because we are going to have more meters, sensors, communication networks, so there will be more kind of risk for the cyber insecurity. Okay, so here we have to take a cyber physical modeling or view of the smart grid. Now looking at this graph, so we have a solid lines representing the communication interface among different sections, different equipment, different subsystems of the smart grid. And besides, we have the electrical interface denoted as the dashed line, okay? So clearly you can see we have generators, transmission lines, distribution lines, and the customer loads. These are certainly connected by the electrical circuits. So the power is generated from the plant, transmitted over the transmission grid, distribution grid, and delivered to the customer appliances. But in the meantime, we also need to have the communication network for these different segments. So as represented here, you can see that in order to operate and monitor the whole power grid, we should take measurements of the generators, transformers, transmission lines, cables, distribution networks, as well as the customer meters. So these data are collected by the central operator of the system. And in the meantime, the electricity is also traded in a market. I'm not sure whether India has an electricity market, but in Singapore, we do have a wholesale electricity market. So in order to participate in this market, the power plant, they have to bid in the market to sell electricity. And the retailer will also buy electricity in the market and sell it to the customer. So all of this market transaction has to be based on the real-time and accurate, reliable communication. So you can see that the market is exchanging information and data with the generation plant, power grid, as well as the retailer and the customer. Okay, and not to mention the operator. The operator certainly they need to have all the information of the system in order to do the dispatch, to do the real power dispatch, reactive power optimization, network reconfiguration, and even the maintenance, right? And besides, for a smart grid, there may also be service provider. And this service provider may aggregate the flexible loads together to provide the ancillary service to the power grid. Remember this morning when I introduced the REITs project in Singapore, we are actually aggregating the individual small microgrid system together to provide ancillary service to support the power systems, frequency control, and peak shaving, so on and so forth. So the service provider will also communicate with the different segments and parts of the system. So as I just introduced, the PMU are actually installed at the generator plants, power grids, and even distribution grid. So the PMU are mainly for the power grid application. But the smart meter, on the other hand, are actually installed at the residential sites. So they are installed directly at the household of our customers, and they will take measurement of the power profile and some other information. And this information, along with the PMU data, are used by electricity market, system operator, as well as the service provider. So you can see that in such a way, the smart grid is a cyber and the physical coupled system. Okay, so we do need to analyze both layers, cyber layer and the physical layer. So that is, the general idea behind this. Okay, now, so why do we need AMI, advanced metering infrastructure? So you have to know that traditionally, there is only a single way of information flow between the utility company and the customer. So basically, the utility company, they installed the energy meters at the customer site, and every month or every quarter, they come here to take the measurements to check how much energy the customer have used. Then they will issue a bill to you, right? So you can see that this is just a single way flow of the information. Only the utility company can take the measurement of the customers, but the customer cannot feed back their information to the utility. Okay, so that is the traditional practice. So in order to enable a two-way flow of information between the consumers and the utilities, we have to build up this advanced metering infrastructure so that the customer and the utility company, they can communicate, they can talk to each other. The customers, they can take the control order or other information issued from the utilities, and then they will respond to this control order or this different information. So this is called demand response. Okay, so you can see that AMI is mainly to support the demand response. demand response. And besides, it will also allow the service provider to control the consumer's electricity usage through a direct load control scheme. For example, if the utility company, they can directly control your plugs, electric plugs, or can control your electric appliances directly through this AMI, they can, um, directly shed the load or turn on your load in order to operate the whole power system in a better way. So the AMI can also support the direct load control. All right. And clearly, all of this demand response and the direct load control is to facilitate the smart grid technology, to facilitate the renewable energy resources utilization, as well as to support the distributed generation. Let's say the rooftop solar PV and some other clean energy installed near the customer site. Okay. So in other way, the AMI is enabling infrastructure to support demand response and the consumer's participation in the smart grid operation and control. So that is a major motivation for the AMI. But clearly, what is AMI? What is the definition of the AMI? So generally speaking, the AMI consists of three parts. Okay, the first part certainly is the smart meter. Okay, the smart meters are installed at the household level in the, let's say, the residence or in even the factories or commercial buildings. Okay, so this smart meters hardware, they have to be placed in this customer site. And there must be a communication network between the consumers and the service provider. So we do need a communication link, and different communication technologies can be used. For example, fiber communication, power line communication, or even wireless communication. Okay? And certainly the internet-based communication can also be used. Last but not least, okay, when we collect the data, when we measure the data, and when we transmit the data from the smart meter to the service provider, so how can we analyze this data? So we need to have the meter data management system. This is more like a software system. So this MDMS can store the data, visualize the data, analyze the data, extract the information or knowledge from the data, and then make use of the data. So clearly, smart metering is a key component of the AMI. After this section, I will introduce more details about the smart meter. The communication network between the consumers and service providers is also called AMI host system, okay, because it's a communication network, and different protocols can be used. For example, model bus and some other communication protocols. So here we have to be very careful, because when communicating the smart metering data between the consumers and the service providers, we have to make sure this communication technology is secure enough, robust enough, so as to mitigate the risk of cybersecurity. And this MDMS, as I said, is more like a software system which can receive, store the meter data, and perform advanced analytic functions. So that is how MDMS look like. Now here, let me show this illustration of AMI structure. So here you can see at the meter site, we have, smart meter for electricity. And besides, remember, when we talk about energy internet, we want to integrate different energy systems together. So sometimes we may also install the gas meter and water meter together with the electric meter and make it as a whole smart metering system. Okay. So at our university, we actually have such a integrated metering system, which can simultaneously measure how much electricity, the power is consumed, the gas consumption, as well as the water, so that we can have a better understanding of how the energy and the resources are being consumed by the customer. So that is metering devices, okay, metering devices. Communication network, okay, as I said, different type of the technology can be used. such as broadband, power line communication, and even power line carrier. Okay, we can directly use the power cables as the communication medium. And the traditional radio frequency mesh network, right, and the new technology WiMAX technology, they can all be used for this AMI. So depending on their availability and depending on their cost, investment cost, so we can choose different communication technology. And the MDMS, okay, the software system. So here we can have many more inventions and functions. Okay, so while the communication network, the meters, they are more hardware. The MDMS is more like a smartphone app. Okay, with the data as the input, we can do a lot of functions. So many researchers in the smart grid area, they are actually working on this area. After they get this smart metering data, they can, kind of extract the customer patterns from the data to know better of how the consumers is using electricity and as well as natural gas, water, so on and so forth. So that is, you can see here, the MDMS, it can be done by the utility and it can also be done by the third-party service provider. Okay, just like the smartphone app. Okay, so people can develop their own app and upload to the platform for people to use. Now, the benefit of the AMI, very clear, right? We can support a two-way communication between the customer and the utility. Okay, and importantly, sometimes for the communication network, we can further divide it into wide area network and home area network. The home area network is more internal. Okay, it is just communicate the appliances within a home. Then the wide area network is to communicate the household with the external system. Okay, so here we can also divide the communication into two parts. Then, the benefits are very clear, right? We can have more data, we can have more information, we can perform more smart grid functions, and we can have a better situational awareness of the customer, the increased visibility, right? It can also support the systems operation, asset management, so on and so forth. So let me show you the home area network as this example. You can see here we have this smart meter, and we have different appliances, laundry machine, refrigerator, the lighting, and the air conditioning, the solar PV inverter if we have installed at the rooftop, and the energy storage system, or even the electric vehicles, right? So all of these appliances, they are interfaced through this dashboard. They are interfaced through power line, of course, but in the meantime, they are interfaced through this communication network, this AMI. And this internal communication network is called home area network. Okay, home area network. Then the smart meter will collect all the data together, Then the smart meter can also communicate with the utility network through the wide area network. Okay, one network. So this is how the smart meter and the AMI, as well as the communication infrastructure, is implemented in reality. Then, so after this AMI infrastructure, I will mainly focus on the smart meters, and I will show two application examples of the smart meter in real world. Okay, so first of all, before we introduce smart meters, let's take a look at the traditional meters. I suppose everybody is familiar with these mechanical devices, right? So they are installed in our households, our buildings, and clearly you can note the unit of these meters are kilowatt hour. Okay, kilowatt hour is the energy unit. So it shows how much energy has been consumed since the meter is installed, right? So clearly there is no power information. Power is the instantaneous value of the energy. Okay, it is the differential of the energy over a time period. So clearly this mechanical meter do not show power information. And in terms of the sampling, this meter is automatically running as long as energy is consumed. It will, the numbers will change. So the sampling rate depends on the utility, depends on the crew, okay, utility crew. Sometimes they come every month to take note of the number, and then they will issue an electricity bill. Right? Sometimes they can do a weekly based, monthly based, or even quarterly based. So the sampling rate of the traditional meters are either low or kind of automatic. And there is no communication. There is no communication between this meter with the utility company and the service provider, because this meter is just installed there. So you have to manually read these numbers on the meter. So that is how the traditional meters are looking like and how they are used. Mainly they are for the billing purposes. But smart meters are very different. Okay, smart meters are kind of digitalized meters. You can see these are some examples. Unlike very differently from the mechanical meters, you can see they are highly digitalized. Right? They have a lot of functions. They can measure a lot of information. So basically, these smart meters can measure the power profiles, okay, over a certain time. And they can store this data, and they can also transmit this data to the data server. And very importantly, these smart meters, they have a very high sampling rate. They can take the measurement every 30 minutes or every 1 hour, or even you can set the sampling rate to be minute level. Every minute it can take a value. However, if you set the sampling rate too high, you have to have a large memory size in order to store and upload this data. So that is how smart meters look like. So nowadays, these smart meters are very cheap already. So everybody can, actually for many new buildings, new developments, the utilities companies, they are all installing these smart meters. Even in our university, our lecture room, and our student halls, they are all installed with these smart meters. Okay. Now, let's say smart meters, the difference between the smart meters and the traditional meters. Okay. First of all, the most importantly is the traditional meters, they do not have the time stamp. Okay. It depends on the utility crew to read the meter, to read the data. But the smart meter, they can take the time step of the energy consumption so that they can measure the power profile of the customer. Okay, they can measure the power profile. Later, I will show an example. And another very important difference is the smart meter can support bidirectional or two-way communication with the utility communication network through this AMI. Right? At the home area network, this smart meter can, communicate with different appliances, and then it can transmit the data to the utility communication network. This is the most important. These two are most important differences. But here, let me show you some practical examples of the smart metering data, which are collected in Australia. Okay, back to 15 years ago when I was in Australia doing my PhD research, we have a project for smart metering data analytics. So at that time, we have installed 5,000 smart meters in a city called Newcastle. Okay. Then we have collected the customer's data and perform some data analytics. So here are three examples of different customers. So each blue curve stands for a power profile of a day. And the sampling rate is 30 minutes. So every hour it takes 2 measurements. So you can see here, every day it has 48 points. So this curve, every curve has 48 points. Now, each curve represents a day, okay? Now, the 3 customers, at a very quick glance, you can see that the 3 customers, their power consumption profiles are very, very different, right? So for the first one, you can see for some time, during this time period, the power consumption is quite low, and during this time, the power consumption is high. right? And for this customer, you can see that, oh, this power profile always looks like a triangle, okay? It's a increase to a certain limit and decrease, the increase and repeat, repeat, repeat. So it's more like a triangle type of power consumption profile. And this one is another, this customer is also different. Sometimes it has a triangle, and sometimes it has a kind of flat power consumption profile, trapezoidal type of the power consumption. Okay, and another important observation you may note is that even for a single, the same customer, right, for different days, the consumption profile are different, especially for the first one. You can see for some time, this one period is low and this period becomes high. So from us, we may try to analyze the pattern or the kind of behavior of the customers from the data. Now, without any analytical tools, if we just manually or visually inspect the profiles, what can we observe? Okay, so for this one, right, so my first guess is that, okay, for some seasons, probably during the summer season, right, these customers does not need the air conditioning, so the power consumption is low. But during the winter time, they may use the heater. They may use a heater during this period, so the power consumption becomes high. Okay. Wait a second, I can see some students just raise hand, right? You have questions, right? Anyone has questions? I just see you have no questions. Okay, let's continue. So yeah.
Professor, is that plot is for a daily profile?
Oh, it's power. It's not voltage. Sorry, it's power. It's a power. Okay, the y-axis is the power.
No, I'm talking about x-axis, Professor.
What?
X-axis.
X-axis is the time. Yes, it's the time. The time index from 0 a.m. To the 12 a.m. Yeah, every day 48 points because the sampling rate is 30 minutes. Okay, so that is for the first customer. Then how about the second? The second customer, why it always has a triangle type of profile, power profile. So let's try to guess which type of appliance looks like this. Now, somebody may suggest air conditioner, right? The air conditioning, they actually operate in such a way. When the temperature is set, the machine temperature compressor will operate. It will draw power, consume power, then lower down the temperature. And once the temperature setting is achieved, it will slow down, right? The compressor is slowing down, and then it even stops. And after that, when the temperature is, restored to a high level beyond the original setting point, the compressor will operate again, right? So this triangle type of power profile probably come from the air conditioner. Okay, now this type of customers, we do not have idea. You can see sometimes it has a very big triangle type power curve, but sometimes no. So just manually inspect and manually guess is not accurate for sure. So we need to have our analytic algorithms. We need to have our kind of methodologies to analyze this data. So later on, I will introduce an algorithm to analyze this data. So before that, that will be the second application. First of all, I will introduce the first application of the smart meter. So remember that in the early morning, we have talked about the operation of the energy system, right? The controllable resources are, if we have distributed generators, micro turbine, diesel generator, they are all controllable, right? Remember this morning. And if we have a energy storage system, we can charge and discharge. They are also controllable. And also we have mentioned the demand response, right? Remember this morning? we mentioned that some customer loads, they may have flexibility. Okay, flexibility means they are flexible to change the timing or the power consumption amount. Okay, so this is the so-called flexible load. Now, question is how can we control this flexible load? Now, one type of the control, as already mentioned, is the direct load control. I remember we have mentioned here, right? Direct load control. What does that mean? That means, okay, if the plugs, electric plugs or appliance, they are directly connected to a control communication system of a utility. So we can, the utility can directly turn on and turn off your appliance directly. And so this is the so-called direct load control. But clearly, this direct load control is not easy to implement because we need to install the specific communication and the controller in our appliances. And then the utility company, they have to manage a huge number of appliances, which is not easy, right? Which is not easy. Okay. So apart from the direct load control, is there any indirect methods to control the load? Okay, is there any indirect methods to control the load? Okay, one way is that, okay, from the utility perspective, if I want to control the load, let's say for a community or even for a university, for example, for a university campus, if I want to lower down your electricity load, what can I do? Now, I can call I can make a call to this customer and asking them to lower down their power demand. And as a return, I may give them some incentives as a kind of compensation, right? I can give you electricity coupon. I can give you a discount. I can even give you, the revenue sharing by doing the load shedding. Okay, so that is another way. But this way can also be cumbersome. We cannot make sure that when there is emergent need for load curtailment, we have sufficient time to communicate with the customer. And we cannot make sure the customer is willing to take our load curtailment order, right? So this is a reality. So there is actually another way, a very kind of effective way based on the electricity price. Because, essentially the electricity is a kind of goods, right? Everybody is consuming these goods, paying a fee. So if this goods is too expensive, now the customer, they may consume less. Yeah, if the goods is very cheap, then the customer may tend to consume more. So that is a kind of economic property of a goods. Now electricity is the same. If we can set a higher electricity price, now the customer tend to use less. If we set a lower electricity price, then the customer tend to use more. Am I right? Now, the question is how can we accurately, systematically model this whole process and implement this process in reality? Now, this part of demand response based on the price is called PBDR, price-based demand response. Okay. The working principle is showing in this graph. So you can see here the utility company, if they want to indirectly control the load, they will notify the electricity price of the next few hours or even the next day to the customer. And they can send this electricity price through the smarter meters and the advanced infrastructure, the metering infrastructure, because they can directly, communicate with the customer. So after receiving this electricity price notification, then the customer will adjust their electricity usage. Now, clearly, based on the electricity price, if the price is higher than euro, then the customer probably will lower down the demand. If the price is lower than euro, the customer will increase their load, right? So usually the utility company, they will give you a kind of series of the electricity price over a certain period. For example, over the whole day, 24 hours. Then according to the price range, as a customer, I will schedule my own electricity usage. I try to use less electricity during the high price period, and I try to use more electricity during the low price period, right? So by doing this, the power grid can achieve the load shifting, peak shaving, and other functions. For example, if the power grid company they estimate that tomorrow during the noon we will have very little, during the noon period of tomorrow we will have much solar power. So I want to make sure the customers will use more power during that period so as to consume the solar PV power. So I will set a low price during that period. And during the night, when we have no solar PV, the price should be set higher so the customers will use less. So that is the basic, principle. But importantly, you have to understand this price-based demand response is an indirect way, okay? It's an indirect way to control the load. You can see that it allows the customers to manage their electricity usage flexibly, okay, without being controlled directly, okay, without being direct. So this type of demand response is more flexible and more realistic and easier to implement. Okay. Now the challenge is how can we effectively set the price? That will be an issue. Now usually we have a fixed price, right? So most of the case, the price is fixed. No matter when you use the electricity, the price is always the same. And another one is the time of use price. You can set the price at different time periods. Okay, you can set the price at different time periods. This is called time of use. And another one is called the real-time price. You can set the price very differently over a day. Okay, so here you can see this example during the evening, midnight, the price is set very low, and during the noon period and the peak period, it was set high. So the price-based demand response is based on number 2 and number 3. By changing the price at a different period, we can indirectly change the electricity load consumption. So this is a general, idea. Okay, I think before we move to the mathematics, let's have probably 5 minutes break. 5 minutes break. Then we will move to the more technical details. Okay.
Okay, teacher.
Okay, hello everyone. Let's continue with the lecture, the price-based demand response. As I briefly introduced, the main idea of the price-based demand response is to indirectly change the electricity load by adjusting the electricity price. Right? However, in order to make this process accurate, we have to make a mathematical model. So one of the basic model is based on the price elasticity. So here you can see this formula. We use PD T to denote the power demand at a certain time period T. Okay, and then the price PRT epsilon, the order of epsilon. The PRT denotes the price at a certain time period, and the epsilon, the order value epsilon, is the so-called price elasticity. Okay, and the A is just a constant value mapping the price and the electricity demand. You can just take it as a unit value as per $1 for each kilowatt hour. Okay, now question is we have to get the value of this epsilon. We have to get the value of the epsilon. In other words, when the electricity price changes, how much the demand will change accordingly. Now, certainly this price elasticity has to be analyzed based on the customer surveys. So back to Australia, many years ago, we have done such a customer survey, and it turns out that this elasticity price, the price elasticity value is around negative 0.38. So importantly, you need to understand this value has to be a negative value because when the price increase, the demand will decrease. Okay. Now let me show how this relationship of the price and the demand look like in this curve. Okay, in the table values, now if the price is 100%, I mean, if this is original electricity price, correspondingly, we have 100% low demand. So this is the base value. Now, if we increase the electricity by 10% to be 110%, now, according to this price elasticity value, the load demand will become 98%, which decreases by 2%, right? And if we increase the price by 20%, you can see the demand become 96.2%, which decreases by 3.8%. Now you can calculate different values according to this formula. And reversely, if you reduce the electricity price by 10%, for example, you set the price as 90% of the original value, you can see the load demand increase by 2.3%. Okay, and correspondingly, we can draw this curve. We can draw this curve here. Now, this is a kind of relationship between the price change and the load demand change. Okay. Now, if we have this price elasticity value, then from the utility company perspective, they are able to set different price so as to change the corresponding electricity demand. And this is a so-called price-based demand response. Right? Now, I mean, more technical details, more mathematical details, more analysis are actually presented in this paper published in IEEE Transactions on Smart Grids back to, 7 years ago, 2017. So if you are interested, you can download a copy of this paper and read more details in it. Now, here I would like to just show the some results of the price-based demand response to give you a better sense of how it will work. Now, we compare the electricity consumption curve of a day between the price-based demand response scenario and the scenario without price-based demand response. The blue curve is the original load curve, and the orange curve is the one after the price-based demand response. So clearly you can see the difference. Okay? So during the midnight, we try to encourage the customers to consume more electricity. So during this period, we will set a low electricity price. Okay. And also during this period, around 11 a.m. to 3 p.m., we also encourage the customers to use more electricity. So you can see that the power consumption is more. That means we also set a lower electricity price during this period. Okay, when I teach this course at the NTU, some students ask me, "Oh, sir, why we want to encourage the consumers to increase their power consumption during the peak period, right? Because you see here, this period during the noon period is a peak period. Because sometimes we want to do the peak shaving. We want to shave the load during the peak period, but why you want to increase the load? Now, the answer is, during this peak period, we actually will have more solar PV power output. And this solar PV output is almost free of cost, right? So that's why we want to encourage people to use more clean energy during this period. This is why we set a lower price during this period. And then after that period, during this peak period in the evening time, you can see that we actually discourage the customers to use more electricity. That is because during this period, we will have no solar PV because there is no sunshine anymore. So we set a higher price during this evening price. So I hope you can get an understanding how the electricity price can be used to indirectly change the electricity consumption. Okay, so this is the first application of the smart meter. Now, second application, also a very important and useful application of the smart meter, is to analyze the customer's usage pattern. Remember that for the smart meter, right, we can collect all the power consumption of a household. Right here, you can see that the smart meter is measures the total power consumption of the home. However, you should realize that it is the measured value is the total power consumption. It's not the individual. Not the individual appliances. So in other words, from the smart metering data, we do not know how much power is consumed by a certain appliances. For example, we don't know how much energy is consumed by our television, how much energy is consumed by our laundry machine. We never know that, just looking at the metering data, right? Because the metering data is, the value is the total power consumption. But the question is there any way for us to disaggregate the total power consumption into individual appliances? Okay, so physically this is not doable because we don't have meters for each individual appliances. But from the algorithms perspective, this is possible. This is doable. Okay, so the basic idea is, if we are able to disaggregate the total power consumption into the, let me use this one. If you're able to disaggregate the total power consumption into individual appliances, we are able to know when the appliance is on, when it's off, how much energy is consumed by this appliance, right? So this is the so-called disaggregation of the power. Okay. Now, if we're able to do that, we will know we don't need to install a separate meter for each appliance, which is called intrusive monitoring. Now here, we don't install any additional meters. We just use our algorithms. And this approach is called non-intrusive load monitoring. Why is it called non-intrusive? It's because we don't install additional meters, right? We don't break down the original power consumption, the power connection, and we do not put additional sensors. What we do is just based on the algorithms, just based on our analytical approaches. Okay, So this is the so-called non-intrusive load monitoring. And this is also a very hot research topic. Back to 10 years ago, many researchers from either power engineering and computer science, data analytics, data scientists, they are all doing this. They are all based on this technology. And after that, there are already many commercial applications for this non-intrusive load monitoring. Okay, and I will show you an example. I mean later, not here. I will show here the value. I mean the benefit of this non-intrusive load monitoring. Okay, if I'm able to disaggregate the total power consumption into individual appliances, we will know how much power is and energy is consumed for each appliance, right? So here is an illustration of the non-intrusive load monitoring results. So you can see here, for such a big building, okay, almost more than 1/4 of the power and energy are consumed by HVAC, heating, ventilation, and air conditioning. Okay, by the air conditioning, and another a quarter of the energy was consumed by the lighting systems. Okay, by the lighting systems. And besides, another around a quarter was consumed by the rental suite. Okay, by the rental suite. And another, for some other portions, you can see that the dishwasher consumes a portion, right? The office consumes a portion. Clothes dryer also consumes a portion. The wall oven only shares a very small portion. The fridge, refrigerator also consumes a portion. You can see all these data are actually analyzed based on the non-intrusive load monitoring. In fact, we do not put the direct meters and sensors to them. Now, if you know this information, we can do a lot of things. From the customer's perspective, we will have a better understanding of our electricity bills. Okay, so here I can see we have spent too much on the air conditioning. So if I want to save energy, if I want to save electricity bills, this is a potential. I try to lower down the usage of the HVAC, right? And besides, after knowing this information, I can take advantage of the time of use tariff. Because remember, time of use tariff have a different time price of a day, right? So I can match my appliances again to this time of use price, so as to reduce my electricity bills. And certainly I can achieve energy saving, right? I can achieve energy. I know too much power is consumed by the lighting, so I can try to avoid use the unnecessary lighting. Okay, so the benefits is very clear for the customers, and it's also very useful for the utility companies. Why? That is because, okay, from the utility company, if I know better of my customers, I can do better either customer rebate or incentive programs or even other electricity tariff programs. Not just looking at this customer, okay, if I was a utility company, I can see that, okay, this customer consumed too much for HVAC and the lighting system. So I can, design a new electricity package to this customer, okay, encouraging them to use less HVAC to save, energy and carbon emission as well. And besides, if I know the customer behavior, I can also improve my capacity planning. Okay, so look, if I know the customer will have a much kind of energy consumption from the electric vehicles, then I have to plan my electricity network. I have to expand my substation, the transformer, so on and so forth, to support the faster growing power consumption. Right? So we can identify, we can understand the customer behavior and to support our network planning. And another very important value is to identify the appliances that could participate in the demand response. In other words, after knowing this, I can identify which type of appliances has the potential for load flexibility. okay, for the load flexibility. So if I can see, oh, these customers has a very big HVAC load, but HVAC certainly is very flexible in terms of the power consumption, right? We can slightly set the temperature settings to 1 degree higher without affecting the customer's comfort. So I can do this. I can encourage the customer to set 1 degree higher for the temperature setting so as to save energy. Right? But if the result is, okay, this customer only has a very, very small HVAC load, then there is no point to do so, right? Because the load, HVAC load is too small. Even it is flexible, I mean, the quantity is too little. Okay, so that's why the non-intrusive load monitoring is both important for utility company and for the customers. Okay, now I would like to introduce a realistic project conducted at my university for this non-intrusive load monitoring. Okay, so in fact we do not because our campus is office and research labs as well as lecture rooms. So it is unlike the residential loads. Okay, it's unlike the residential loads. We don't have laundry machine. We don't have a television, right? So for this project, we actually are focusing on the chiller plant load, a chiller plant load, because remember in the early morning when I introduced the energy internet in Singapore, a large part of the energy consumption come from the cooling purposes because the temperature is always high. Right? So in this building on our campus, it's called Clean Tech 1 building. There is a big chiller plant. This chiller plant can produce cooling air, cooling water, okay? And I mean, for the air conditioning purpose for the whole building. However, this chiller plant actually has 4 subsystems, which are respectively chiller, condenser water pump, cooling tower, and the chiller water pump. Okay, it contains 4 subsystems. However, these 4 subsystems, they are integrated together. We do not have submeters. Originally we don't have submeters for each of the 4 subsystems. However, we want to know the behavior or the pattern of these 4 subsystems. We want to know which subsystem consumes more energy and what does this energy consumption profile look like, so that we can improve the efficiency of the chiller plant. So here we can apply the non-intrusive load monitoring, right, technology. So we collect the metering data of the chiller plant system. Okay, then we apply our non-intrusive load monitoring algorithm. And finally, we figure out this is the corresponding power profile of different subsystems. And clearly, you can see that most of the power come from this chiller, right, in the order of 600 kilowatt, then followed by this condenser water pump and the chiller water pump. While for the cooling tower, you can see the power consumption is much less. However, this cooling tower, the power consumption is highly fluctuating. You can see a lot of spikes there. Okay, a lot of spikes there. So by doing this non-intrusive load monitoring, we are able to disaggregate the total power consumption of the chiller system into different subsystems. Now, later on, after this project, we design some new control system for the chiller so as to improve the whole energy efficiency of the chiller system. Okay, so this is a general idea for the non-intrusive load monitoring. But I do believe many students are curious about the algorithm. How can we disaggregate the total power consumption into individual appliances? So here I can just tell you a brief, the general idea. The general idea is to apply artificial intelligence. Okay, artificial intelligence. So the problem can be modeled as a classification problem, right? Originally, you can see if we have 1, 2, 3 appliances, each appliance has 2 status, on and off. right? When it's on, the power consumption is a fixed value. When it's off, it becomes 0. So the total power consumption is a kind of combination of different appliances, including their status and the power consumption values. So if we have a large data set, historical data set, we can train a machine learning model, artificial intelligence-based machine learning model. And this machine learning model can tell you when given a certain power profile, it can tell you which appliance is on and which appliance is off. And based on this output, we will know the individual power consumption. So this is a general idea behind the AI-based non-intrusive load monitoring. Okay, so if you are interested, there are many papers on this topic. You can even check this paper. This is also our paper back to 2016. Okay, so a lot of algorithms have been reported. But the key here is the accuracy. Okay, for some particular or very complex household which contains a large number of different appliances, accuracy may not be good enough. But for this one, for this chiller plant system, we can achieve accuracy over 98%. Okay, because the system is not so complex, it only contains 4 individual systems, right? So the accuracy is quite satisfactory. So that is about non-intrusive load monitoring. Okay, now we have introduced the 2 applications of the smart meter and the AMI. But every coin has 2 sides, right? When we have an upside, there must be a downside. So what will be the downside of the smart meters and advanced metering infrastructure? We have already briefly mentioned this in the first day. That will be the risk of the cyber attack, okay? And also the privacy issues. Okay? Intuitively speaking, if we can collect the smart metering data, we can immediately determine whether someone or the resident is at home. Okay, now if we can determine this, it will be a kind of safety issue, right? The thieves can steal the into the household, okay? And if we know the data, we can determine the usage pattern. For example, just like this one, the illustration one, if we know their smart metering data, we will know how this customer is behave every day, when he leaves home, when he come back, okay? How much energy is used. We can determine the status of the customer. This will also be a privacy issue we have to carefully consider about. Okay. And apart from the privacy, another important risk is the cyber attack risk. Okay, you can see that the smart meters, they are installed at the household level, right? And they are connected with the AMI, home line network, and later on the wide area network. So if there is a hacker, if there is some technology can inject or hack into the smart meter or hack into the communication network, then it could be very dangerous. Why? Because we can inject the false data. We can inject the false data. For example, originally the real value, the true value of the metering is, let's say, 10 kilowatt. However, I can change the 10 kilowatt into 20. I can even change it to 0. Right? If I change it to 20, now the customers, they may need to pay additional bill. They may need to pay more bills to the utility. But if I can set it to 0, I don't need to pay. Then the utility company will lose money. Right? So this is the so-called false data injection. Okay, the hacker can try to inject a false data into the metering system. This could be very dangerous. And besides, they can also do a so-called denial of service attack, DOS attack. What does that mean? That means, okay, if I can hack into this smart meter, I can try to turn off the appliance. I can try to kind of cut off the communication between the smart meter and the external WAN area network. So this will also affect the customers. Okay, so in the power smart grid area and even computer science engineering area, many people are working on this false data injection and the deny of service detection and defense. Okay, so here are actually two steps. The first step is to detect. We need to detect whether there is a false data. We need to detect whether there is a denial of service attack. Okay. Now, in order to do this, we can also apply artificial intelligence. Now, here in my research group, we have just developed a artificial intelligence-based method to detect the false data injection. Now, here is some examples. Now, you can see this is original data, original metering data. Looks like this. Now, we can inject some false data into the original data. And depending on the order of the injection, we can have different levels of attack. Now you can see the level 1 attack is very minor. Visually, you may not distinguish the two, right? But the level 2, level 3, the attack order is higher. You can see clearly level 3 is very different from the genuine data. And the level 2, if you look carefully, you can see the difference. But level 1, very difficult. Okay. Now, here we apply artificial intelligence to detect whether the metering data contains different attack level, different levels of attack. Okay. So this is also our latest research works. Then the question is also again, I mean, after the detection, after you detect this false data, you have to defend your meter, right? You need to compensate the false data. You need to filter out this false data. You need to restore the original data. That is another important topic to do. Okay, but anyway, I think my major point here is that when we deploy the smart meters and the advanced infrastructure, metering infrastructure, we need to carefully consider this security and safety issue. Okay. So practically, the utilities, they should considering the following risk at the onset and during the AMI program deployment. We need to be very careful to select the vendor and the product. Right? Sometimes the vendor will intentionally place some kind of risk issue in their products. And we need to integrate the AMI network management and the system together. And we need to cooperate the governance and the regulatory compliance. There must be standards, protocols, right, to follow. And we need to consider the privacy and the integrity of the data. There must be some policies and even laws for this data privacy and data integrity. Okay, and we need to have a good identity and access management system. Not everybody can access to this data set, the data server, so on and so forth. And in terms of the physical operational control infrastructure security, we also need to evaluate them carefully and do the remediation schemes. And the web services and the portals, they must be encrypted, right? They must be protected. And the business continuity and the resilience, okay, if this is a third-party service provider, we also need to consider this as well. And the security events and network monitoring, certainly it has to be continuously monitored on a 7-day, 24 hours, and yearly basis. Digital investigative assessment. Okay, this comes from the digital perspective, and also we need to consider the vulnerability. We need to evaluate the vulnerability of the whole system as well as identify the potential threats. So this is, I mean, many security issues we have to consider. All right, I think that is the end for the smart metering part of today. So tomorrow I will introduce the phasor measurement unit, which is for the power grid application. Smart meters are more for the customer application, as we introduced today. Now, since we still have several minutes, please let me know if you have any questions. We can any questions, please?
Professor, in the chat box, some participants have given
Okay. Let me check. Okay. How am I ensure privacy and user data maintaining privacy? Any private? Yes, as I mentioned, as I introduced, okay, in order to maintain this, ensure the privacy, we have to consider all of this. There must be some protocols and standards to follow, right? Standards and protocols to follow. In Singapore, yes, there is a very comprehensive and systematic national standards when you deploy the smart meters and when you collect the customer data. They have to follow all the policies and standards as well as the protocols. Yeah, implementation of the AMI, I think basically it should be the privacy and the security concerns. And for the cybersecurity, they are kind of they are doing this hardware and software based. Hardware, they do a lot of kind of firewalls, and the software based, they do this kind of attack detection algorithm deployed to the meters and the system. Yeah, I think that is one. Let me know about the software mentioned in the smart grid communication. Oh, okay. Oh, sorry, I haven't. Give me 1 minute. I will search that report because that research was done 15 years ago. So I really forgot the name of the communication simulation software. But let me let me check. I will send to the chat box later. Then false data injection by using algorithm. Yes. For this, research work, you can hear for this paper, we are able to identify all the attacks at different levels, even the level 1 attack. Because this one, we use a very advanced artificial intelligence. We use a very advanced artificial intelligence. Let me. Okay. Let me check this communication. Any other questions you want to ask?
Professor, I have one question.
Yeah, please.
Yeah, how about the measurement of the harmonics in the smart meter?
The smart meters, it may not measure this. Sorry, the harmonics may not be measured. Harmonics may be measured by power quality sensor, PQ sensor.
Okay.
Yeah,
but there is in the smart meter there is no limit of allowing the harmonics in the system also.
Yeah. In the harmonics, okay, if we have the electric vehicle chargers, the sources interfaced through power converters, it will inject a lot of harmonics. But the smart meters cannot measure that. Yeah, only PQ sensors can do.
Okay.
Okay. Okay. For the student, I remember what we have used in that project. We actually use this OPNet. We use this OPNet. So you can see this is a list of different network communication network simulation. In our project, we actually use this OPNet, but you can try others. And even the MATLAB, I remember even the MATLAB, there is a toolbox. There is a toolbox to simulate the communication system. You can, there is a so-called communication system toolbox. I just did a quick search. You can see that here, communications toolbox. It can also simulate different, the communication flow, different type of the topology, so on and so forth. You may try this as well. Yeah. All right. Any other questions?
Sir, how can we distinguish between faults and cyber attacks?
Okay, very good question. So you have to know that even for the cyber attack, essentially it will lead to a physical attack, a physical fault. For example, if we attack the power generator, it will become outage. If we attack the transformer, it can also be a branch outage. So from the power grid perspective, in the end, we have to take this as a physical disturbance. So we cannot unless we can root the source of the disturbance. We don't know whether it's caused by a physical accident or cyber attack. But essentially, from the power grid, it will experience the physical disturbance. Yeah. So for the Euroking outage, it is was founded. Post the outage investigation that it was probably caused by cyber attack. But during the event, we may not be able to know.
Thank you, sir. Sir, I have one more query. Sir, for that co-simulation, if we have communication thing in MATLAB also, so we need not to use, we can do co-simulation in the same platform, Simulink.
Correct. Yes, in our original project, we do the co-simulation. We did a coupled cyber physical system. So every time we do the power frequency control simulation, and in the meantime, we take the signal from the communication system. Then we simulate the time delay, because the time delay is very important for the power system from the dynamic operation perspective. Yeah.
Okay, sir. Thank you, sir. Thank you so much.
Thank you. Can you suggest a few smart meters with open source software to understand IoT? Smart meters, if you want to get a kind of physical item, you can just go to the website. There are a lot of vendors, and they are very cheap as well. Yeah. So open source software, I'm not sure whether there is open source software for smart meter. But if you want to do the kind of smart meter data analysis, there are a lot of. You can go to GitHub. You go to GitHub and search smart meter data analytics. There are a lot of algorithms. Let's say for residential load forecasting, load disaggregation, so on and so forth. You go to GitHub, there are a lot of resources. And since the smart meters are mainly connected to dedicated secure standard network. Yes, you are right. Smart meter infrastructure are connected to a standalone network, but sometimes it may not. The things is changing. In the past, yes, it's a closed industrial network, but nowadays, when people want to install more distributed energy resources, let's say rooftop solar PV, electric vehicles, or even home residential batteries, they sometimes use the internet network. They even use, let's say, other network, for example, the WebEx, right? They use a different type of the communication. This network may not be kind of standalone. They are actually open network. So the risk will emerge. And if the blackout occur due to cyber attack, what will be the backup? Just like the previous question, essentially the power grid will experience physical disturbance. Okay, even let's say we do this deny of service. Okay, we can do the deny of service. We can take down one substation. We can take down the generator. Now the restoration and the recovery will be the same. Right? Will be the same. We still need to do the emergency reserve. We still need to do the let's say network reconfiguration. or even the emergency power supply by the mobile battery bank, so on and so forth. Yeah, but our idea is that we need to protect our vulnerable devices against the cyber attack, so that it will not lead to the physical disturbances. Yeah.
Any questions?
Yeah. Any more questions?
Yeah. Thank you, Professor. Thank you, all the participants.
Thank you, everyone. I will see you tomorrow and talking about the physical measurement unit and for the power grid applications.
Yes. Thank you, Professor.
Thank you. Have a nice day. Bye-bye.
Bye-bye.